Tonight, drift into the heart of the Tarantula Nebula, where R136a1, one of the most extreme stars ever studied, glows like a white furnace, carving calm patterns into a luminous cloud. In the next moments, gentle storytelling will turn complex astronomy into soothing images, light, pushing against gravity winds, shaping filaments, elements seeding future worlds. If you love relaxing cosmic journeys that blend wonder with clarity, tap like to help more listeners find this space and subscribe with the bell so you never miss a quiet night among the stars. Take a deep breath, settle in, and let the biggest questions feel small as we begin. R136a1 is an extreme, short-lived star whose story clarifies how nature pushes against the limits of star formation. It sits inside the Tarantula Nebula in the Large Magellanic Cloud about 160,000 light-years away. This matters because weighing such a heavy weight tests the rules that tie brightness, pressure, and gravity to birth, growth, and an early end. By the end, the outline of its mass, its behavior, and its likely fate will feel calm and clear. Picture a crowded nursery of soft blue light, where gas folds like slow surf, and one beacon stands brighter than a city of stars. The early takeaway is simple. An exceptional star in an exceptional place reveals how the universe builds and trims its giants. The Tarantula Nebula is a fierce, fertile region, a vast chamber where shock waves and ultraviolet light reshape clouds into lace. A cluster is a tight family of newborn stars. Here that family called R136 presses stars close together so gravity can gather material quickly, even when radiation is trying to push it away. In short, location and crowding explain how a giant can start. Radiation pressure means light pushing outward with force. Imagine sunshine strong enough to move dust, then scale that force until it tugs on gas itself. Think of a lighthouse beam that not only shines but shoves. This matters because the push from light fights the pull from mass, setting a ceiling for how big a star can remain. The Eddington limit means the brightness where light can balance gravity. A spotlight with more power peels material away. A slightly dimmer lamp lets gravity stay in control. The consequence is that an oversized star lives on a ledge always close to shedding what it gained. A stellar wind is a fast outflow of matter from a star. It streams as a continuous gale, and it erupts as dense clumps like a gusty storm that carries leaves and sand. Why it matters is clear. The wind steadily lowers the mass, changes the surface, and rewrites the ending. In short, light pushes back, gravity holds, and the wind quietly carves the giant down. R136a1 glows in a manner that hints at youth. Hydrogen lines in its spectrum appear strong, a sign that deep mixing keeps fresh fuel near the burning layers. Spectroscopy splits light into colors to reveal temperature and motion. In practice, that means thin, bright fingerprints on a rainbow that tell how hot, how fast, and from where the light comes. This is important because fingerprints can be confused when many hands touch the glass. In a crowded core, the glare of neighbors blends, and the sharp central image swells into a halo. Adaptive optics steadies the scene by bending mirrors to cancel blur from air. Space telescopes climb above the air, letting the star stand alone against black. The payoff is a cleaner measure of luminosity, and from that a steadier estimate of mass. The object remains enormous by any calm account, and that is enough to guide the mind to the right questions. The star's presence changes its neighborhood. Radiation hollows a bubble in the gas, sculpting a soft cavity rimmed by glowing knots. Shock fronts ripple outward like rings on a pond after a stone falls. Those patterns matter because they govern which pockets collapse into new stars and which pockets disperse. A single giant can nurture and hinder at once, nursing filaments into denser threads, while burning away the thin veils around them. In short, one source sets the rhythm for an entire nursery. Time runs fast for such a heavy weight. The core burns bright, the layers mix, and the wind trims the outline all at once so a lifetime can fit into a sliver of galactic time. 1,000,000 years feels long when counted silently, yet for a star this massive it is a brief candle. That brevity matters because the scene we observe is a fresh frame, not a slow fade. Today's mass and brightness will not hold for long. At the heart of the matter sits a near balance. Gravity gathers, light resists, and the result is a living compromise, an uneasy truce drawn across the surface of the star. The mind can keep a simple model, a heavy sphere pressed inward by its own weight, while a flood of light tries to lift the outer layers away. When the flood strengthens, the surface peels. When gravity wins, the layers settle and heat rises. Each change redraws the future step by step. The calm takeaway is that even a record challenger obeys plain rules. Stronger push, stronger peel. Stronger pull, tighter hold. The details carry fine print, yet the outline stays gentle and firm. The promise of this journey stands the path from a raw cloud to a blinding giant will sort into clear stages. The reasons for past overestimates and present revisions will make sense, and the likely endings will rest in measured possibilities rather than noise. For now, imagine once more the blue cradle, a quiet bubble amid filigree gas, and at its centre, a white blaze that hums like a distant chorus. The scene is busy, but the logic is simple. A rare place, a rare balance, a rare life. Next comes the patient craft of weighing the unweighable, and learning what most massive truly means in a crowded sky. The early takeaway is that R136a1 grows inside a special cradle, where gravity turbulence and fierce light combine to make unusually massive stars possible. The Tarantula Nebula, also called 30 Doradus, lies in the Large Magellanic Cloud about 160,000 light-years away, and it is a true factory for new suns. A nebula is a cloud of gas and dust. In this nebula, young stars already flood the region with energetic light that strips electrons from hydrogen and makes the gas glow. That glow is not just decoration. It signals pressure, temperature, and motion, and those conditions shape what kinds of stars can form. A star cluster is a close crowd of siblings born from the same parent cloud. The cluster at the heart of the Tarantula Nebula, named R136, is one of the densest known young clusters nearby. Density means many protostars form and grow within a small volume, so gravity has many hands working at once. That closeness matters because gravity collects material quickly, even while intense radiation tries to push material away. In essence, the nursery supplies both the fuel and the storm that can cut the fire short. Visualize a bright hollow, where hot blue stars blow a bubble inside the larger cloud. The shell of that bubble is wrinkled and laced with knots where gas piles up. Along the rims, shock fronts pass like slow waves on a beach after a passing ship. Each crest squeezes a filament. Each squeeze can begin the collapse that makes a new star. This is feedback the loop where one generation sets the pace for the next. It matters because feedback can both build and hinder carving channels where flow accelerates and clearing low-density paths where material escapes. A shock front is a moving compression in gas. In the Tarantula Nebula, shock fronts arise from winds, radiation, and past eruptions. As they ripple outward, they knead the cloud into denser threads. Picture a sheet being pushed from below by warm air. Patterns bloom into cells and ridges as the push continues. In this setting, chemical composition also plays a quiet role. The Large Magellanic Cloud contains slightly fewer heavy elements than the Milky Way. Heavy elements here mean anything heavier than helium. Fewer heavy elements reduce cooling and set different wind strengths. The result is that stars can shine with slightly different balances of light heat and outflow. The consequence is subtle but helpful. The ceiling on birth mass may lift a little when winds are gentler and opacity changes. This is why the environment is central to the story. The cluster core is crowded, and crowding introduces a second path to growth. Dense cores can drift toward each other and merge or share envelopes for a time. A merger is when two young stars join into one. Even without a full union, close passages stir disks and dump gas inward. The payoff is clear. Paths that are rare in looser neighborhoods become common in this compressed city of stars. That explains how a single giant can assemble more mass than standard models expect under softer conditions. A calm recap helps here. The Tarantula Nebula offers intense radiation, powerful winds and high density all at once. Those ingredients together both sculpt and feed a few remarkable newborns. Observations reinforce this picture. The Hubble Space Telescope reveals fine threads and delicate pillars inside the bubble's rim. The James Webb Space Telescope traces warm dust and organic molecules in the same places where gas piles up. The Very Large Telescope resolves bright knots into tight groups and outlines the inner core of R136 with sharper focus. Tools matter because better detail lowers confusion when many bright points overlap. With each improvement, stars separate cleanly, and the measured brightness of each one steadies. That steadying is important for the question of mass because light is the guide used to weigh these distant suns. In the Tarantula Nebula, the light is so strong that it scours cavities and exposes sculpture in the cloud. Imagine towering ridges that glow along their edges like sunrise on mountain snow. In darker pockets, dust lanes curl like smoke around brighter holes where winds have punched through. These images are more than beauty. They show where gas flows and where it stalls, where the next cores will form and where they will be stripped. Turbulence is the random, swirled motion in the gas. In this region, turbulence seeds a range of clump sizes from small beads to large, loosely bound knots. Gravity wins where a clump grows heavy enough to collapse. Radiation wins where the clump is thin or exposed. The balance shifts from place to place because the cluster is not uniform. The quiet lesson is that stars, even large ones, are products of both nurture and nature. R136a1 near the cluster center finds more fuel, more neighbors and more pressure than a similar core would in a calmer cloud. That central placement also brings more glare, more wind and more stripping. The star remains a negotiation between gathering and peeling. A small payoff arrives here. Understanding the nest explains why R136a1 can begin so large and why it will not remain so. The very conditions that feed the giant also sharpen the tools that cut it down. This symmetry gives comfort. The same physics that builds also limits, and therefore extremes remain rare. A final soft image sets the stage for what follows. See a luminous cavern carved inside a storm of gas, its walls beading with bright knots, its floor filled with a swarm of newborn suns, and at the center a blinding point that hums like a white flame. In that place, the story of an oversized star begins to make sense as a natural outcome of environment rather than an exception. Next comes the patient craft of turning light and motion into a mass, and of learning what most massive truly means in a crowded, shimmering core. The early takeaway is that astronomers weigh a distant giant by turning light, color, and motion into numbers, then into mass. And they do this carefully because crowded scenes can trick the eye. Mass is the amount of matter in a star. Luminosity is total energy output each second. Spectroscopy is splitting light into colors with fine detail. These simple handles open the door. First comes brightness. A very massive star shines with a brightness that climbs steeply with mass, so measuring how much light arrives, correcting for distance and dust, and comparing to trustworthy models gives a first estimate. Visualize a lantern behind a curtain. If the fabric dims the glow, a careful observer judges the cloth lifts the dimming and then reads the true flame. Dust in the Large Magellanic Cloud acts like that cloth, and its pattern varies across the Tarantula Nebula. A small payoff appears here. Because the distance to the Large Magellanic Cloud is well constrained, the main dimming to solve is dust, not distance, which steadies the first step. Next comes temperature and surface gravity. Temperature shapes colour. Surface gravity is the inward pull at the surface. In spectra, certain lines shift shape with temperature and pressure. The shapes are fingerprints. A hot, swollen star leaves broad, strong marks in helium and hydrogen, while a cooler, compact star leaves different marks. By matching the pattern to models, astronomers retrieve temperature and gravity, and from those they infer radius and a refined luminosity. Imagine a prism on a dark bench. A narrow beam fans into a rainbow, and tiny notches line that fan. Each notch is a clue. This is the quiet craft behind the big claim. A calm recap helps: light tells power, colour tells heat, and line shapes tell weight at the surface. A third thread pulls on motion. In rare lucky cases the star has a companion, and both orbit a shared centre. An orbit is a repeating path under gravity. By tracking the period of this dance, and the speed along the line of sight, astronomers can solve for masses using gravity's firm rules. Where two bodies reveal a full orbit, the masses come from geometry and time more than from models. The payoff is strong because dynamics care little about wind or glare. Visualize two bright drops circling on a black pond, leaving ripples that recur with perfect rhythm. When this rhythm is clear, the scale reads true. However, the core of the R136 cluster is crowded, and crowding complicates every method. Many points of light overlap. Blended light makes a single star appear brighter and hotter than it is. A blended source is a sum, not a single voice. Adaptive optics lets mirrors shift shape to cancel blur from air-pressing stars back into sharp points. Space telescopes step above the air entirely. With each improvement, a bright peak splits into several lesser peaks, and a supposed monster becomes 2 or 3 normal giants sharing a line of sight. The calm lesson is that resolution is part of weighing. Better sharpness means a smaller claim, but a sounder one. A second recap lands. Brightness gives a first guess. Spectra refine the guess, and orbits when present lock the answer. There is also the question of when to weigh. Initial mass is the mass at birth. Current mass is what remains today. Very massive stars lose mass quickly, so a snapshot gives a current mass, while models and wind rates help travel back to birth mass. Wind rate is the amount of matter lost per second through the outflow. To estimate it, observers study how certain lines in the spectrum grow asymmetrical, a sign of fast outward flow. The profiles look like a bite taken from one side of a line. That bite shows how fast the wind flies and how thick it is. This matters because the path from initial to current mass depends on wind strength, and wind strength depends on metal content and brightness. The Large Magellanic Cloud has fewer heavy elements than the Milky Way, which may soften winds, and that in turn may allow larger initial masses. Think of a tree in a gentler gale. It can grow taller before trimming begins. Even with such nuance, uncertainties remain. Crowding, dust, wind clumping, and the exact balance between light, pressure, and gravity all widen the error bars. Error bars are the honest ranges around a number. Honesty about ranges matters because it keeps claims from racing ahead of evidence. The phrase "most massive known star" is therefore a living label that changes as sharper images, better models, and new orbits arrive. A small payoff returns here. Even when estimates step down with improved clarity, the star remains an extreme case within the safe guardrails of physics, and that is enough to test ideas that set limits. A visual anchor steadies the mind. Picture a quiet laboratory of the sky, where instruments are scales light is the grain being weighed, and the star is a bright handful placed gently on the pan. Each correction is a brush that sweeps dust off the scale. Each new image centers the pan under the grain. The reading settles not to a boastful peak but to a confident plateau. A third recap completes the scene. Careful corrections, not dramatic claims, turn starlight into mass. Finally comes meaning. Knowing the mass fixes the clock of the star's life, sets the likely sequence of burning stages, informs the strength of winds, and narrows the field of possible endings. This matters because it connects a single bright point to the wider flow of elements and future stars. Weighing the unweighable, therefore, is not a stunt. It is a way to link a local beacon to the long story of cycles in a galaxy. In this light, the title most massive becomes less a crown, and more a marker on a map. It showed where the upper edge of star birth lies today in one place with one set of tools. Gentle curiosity remains for the next task. The balance between gravity and glare deepens into a study of pressure outflow and near limits, where brightness itself begins to peel the surface away. Next comes that balance drawn with care so the outward push of light and the inward pull of mass can share the same quiet page. The early takeaway is that light itself pushes on matter, gravity pulls inward, and their quiet tug-of-war sets a practical ceiling for how massive a star can be. Radiation pressure is the outward force from light on particles. Imagine sunlight moving the tail of a comet, then amplify that push until it can shove gas. The reason this matters is simple. If light pushes as hard as gravity pulls, layers can no longer rest in place. Gravity is the inward pull that grows stronger as mass increases. In a star, pressure from heat pushes outward while gravity presses inward, and the result is hydrostatic balance, a gentle standstill between squeeze and support. When light becomes intense enough, its pressure joins the outward team and helps the gas escape. The Eddington limit is the brightness where light's outward push matches gravity at the surface. Picture a scale with light on one pan and weight on the other. At the limit, the beam sits level. When a star hovers near that balance, even a small brightening can puff the outer layers and raise a wind. A small payoff arrives here. This balance explains why an enormous star lives in a state of near release, steadily shedding what it gathers. Opacity means how easily matter blocks light. A fog has high opacity. Clear glass has low opacity. Why opacity matters is direct. The more a layer blocks light, the more light transfers momentum to that layer, and the stronger the outward push becomes. Heavy elements increase opacity through many absorption lines, like a dense set of tiny catches that light can pull on. The Large Magellanic Cloud contains fewer heavy elements than the Milky Way, and that reduces some of the catches, softening the push. A calm recap helps light pushes, gravity pulls, and opacity sets how hard the push lands. In these giants, the outer layers are not still. They boil, swell, and stream away. Line-driven winds are outflows accelerated when light grabs many small absorption lines in the gas. Imagine a sail with countless tiny ropes that light can tug. The combined pull becomes a steady gale. When the star grows brighter or hotter, more lines come into play and the wind strengthens. Each gram that departs lowers the mass, calms gravity slightly, and makes it easier for the next gram to leave. Outflow is self-reinforcing but not runaway, because the same loss reduces brightness and cools the surface a little, which softens the push. The consequence is a regulated leak rather than a sudden burst. Porosity means the material is clumpy rather than smooth. In a clumpy wind, light threads through gaps, which lowers the average push on the gas. Visualize a lace curtain instead of a solid sheet. More light slips through open spaces. This detail matters because porosity can reduce the effective opacity and allow the star to carry a higher brightness without blowing its outer layers entirely away. A second payoff arrives. Clumping changes how observers read wind strength from spectral lines, which affects how they back-calculate the mass. The envelope can also inflate near the limit. Envelope inflation is the swelling of outer layers when radiation pressure nearly equals gravity. Think of a pot of thick soup heated from below. As bubbles rise, the surface dome lifts and wobbles. In a star, heat tries to rise, light pushes and gravity holds, so the layers puff outward into a larger, cooler shell that still rests on a hot core. Inflation matters because it changes temperature and increases the role of lines feeding the wind again. A soft, bright skin makes the star look larger and shifts the color slightly toward the blue-white edge. A gentle recap lands brightness near the limit puffs. The surface puffs the surface to more lines, and more lines feed the wind. There is also the role of photon trapping. Photon trapping means light scatters countless times before escaping, sharing its push many times over. Imagine a ball bouncing inside a padded room, nudging the padding each time until the room slowly expands. In dense layers, this cumulative nudge helps lift gas and adds to the outward drift. The mind can hold a quiet model, a heavy core holds, while a luminous mantle constantly tries to float away, and the result is a steady flow. For R136a1, the important idea is not a single dramatic threshold, but a moving balance. The star shines so powerfully that parts of its surface approach local balance points, where outward and inward forces nearly match. In those zones, the wind peels layers like soft bark, then shifts as conditions change. Because the cluster's environment is slightly lower in heavy elements, the push is moderated compared to a similar star in the Milky Way. That moderation may raise the birth ceiling a little, but still leaves the star close enough to the limit that winds remain decisive. A small payoff returns here. The environment and the physics of light together explain how a giant can form and why it immediately begins to unbuild itself. Instruments see supporting signs. Broad emission lines in spectra show fast outflows. Asymmetrical profiles signal acceleration. Subtle flickers in brightness suggest surface changes consistent with near-limit conditions. None of these markers alone prove the exact mass yet. Together they form a calm, consistent picture, a star living on the ridge between held and released. A visual anchor steadies the scene. Imagine a lighthouse whose beam has become so strong that it drives mist into a steady stream, even as the cliff beneath it refuses to yield. The cliff is gravity, the stream is the wind, the balance point is the ledge where water forever spills but the stone remains. A final recap keeps the page clean. Light pressure sets the push, gravity sets the pull, opacity sets the grip, and together they fix a working ceiling for mass. Standing on that ceiling, a star does not explode by default. Instead, it breathes through its wind-trading brightness for mass in a continuous exchange. Next comes the wind itself, the long peel that reshapes the star's timeline and sets the stage for its brief, fierce life to follow. The early takeaway is that powerful winds steadily peel, 136a1 lowering its mass, cooling its surface, and guiding its life toward a gentler ending than its birth seemed to promise. A stellar wind is a continuous outflow of gas from a star. In a very luminous starlight grabs atoms and ions through many tiny absorption lines and transfers momentum outward. Picture a sail covered in countless fine hooks. Each photon tugs one hook, and the combined pull becomes a steady gale. This matters because the gale removes mass, and losing mass changes the clock, the color, and the final fate. Observers read these winds directly in light. Certain spectral lines show a signature with a bite on the blue side and a glow on the red side. This pattern, called a P Cygni profile, reveals gas fleeing the star while also shining warmly behind it. From the depth of the bite and the width of the glow, one can estimate how much matter leaves and how fast it travels. Mass loss rate means the amount of material carried away each second. Terminal velocity means the final speed reached far from the star. These are simple handles that point to deep changes underway. A small payoff arrives here. Even without touching the star, careful reading of line shapes shows the wind's strength and the pace of change. The wind is not smooth. Clumping means the outflow gathers into dense knots separated by thinner streams. Visualize snow streaming off a high ridge. Fine powder lifts first, then thicker veils fall away in billows that break into lumps. Clumping matters because dense knots absorb light differently, making the wind appear stronger or weaker depending on how the knots are arranged. Porosity means light can slip between knots, lowering the average push, just as sunlight passes through a lace curtain more easily than through a heavy cloth. A calm recap helps light drives the wind, clumping reshapes the ride, and porosity adjusts the force that actually lands on the gas. In R136a1, the spectrum often shows strong broad features that point to an atmosphere already stirred by fast outflow. As the wind persists, fresh layers rise to the surface. Products of hydrogen fusion appear, notably helium and nitrogen, while hydrogen lines can keep their strength if mixing keeps fuel near the burning zones. This surface change matters because it marks the progress of peeling and flags how far the wind has already carved. Imagine a white-hot tree whose bark is carried away by a warm, continuous breeze, revealing paler wood beneath, while the tree still grows from within. The environment tunes the gale. The Large Magellanic Cloud contains fewer heavy elements than the Milky Way, which reduces the number of lines that light can pull. With fewer hooks, the same light does slightly less work on the gas. The result is a gentler but still decisive wind, one that allows a higher birth mass yet still enforces steady trimming afterward. A second payoff lands here. Environment and wind work together like two hands shaping clay. One allows a large form to rise, the other smooths and thins it back toward a shared shape. Winds also vary with time. On some days the outflow thickens, on other days it thins. This variability can come from patches on the surface, from shocks within the wind itself, or from gentle pulsations in the outer layers. A pulsation is a rhythmic swell and settle. When the surface swells, it cools slightly, changing which lines grip the light. When it settles, the opposite happens. These swings are not storms so much as breathing. They matter because they blur the connection between any single spectrum and the long-term loss. The mind can hold a simple model. The wind is a breathing river, not a rigid pipe. Mechanical energy from the wind also sculpts the neighborhood. As gas streams away, it drives shock fronts into the surrounding medium and hollows the cavities seen around the cluster. Visualize a lantern in a fine snowstorm. The light gilds every flake, and the flow of warm air drives a constant glitter outward, laying bright arcs on the air. Those arcs become real shells in the nebula, where the wind meets the cloud and slows. This feedback matters because it governs where the next generation of stars can begin. A gentle recap returns, winds peel the star expose changed layers, and carve the wider nursery all at once. The wind sets the star's clock. Lower mass eases gravity at the surface, which weakens the wind a little, which slows further loss. This self-regulation produces a long controlled peel rather than a runaway event. The peel cools the surface step by step and shifts the spectrum towards signs of a more stripped, hotter core beneath. In time, such a star can show features often associated with Wolf-Rayet-like states, which means a hot star with strong emission lines and powerful winds. A Wolf-Rayet-like state is a phase of intense stripped brightness. The label is less important than the gentle truth beneath it. The wind has lifted enough layers that the inner furnace whispers at the surface. Instruments confirm the broad picture. The Hubble Space Telescope reports line shapes that fit fast outflows. The Very Large Telescope measures profiles that imply high terminal speeds. The James Webb Space Telescope maps dust warmed by the same massive stars, tracing where energy and wind meet the cloud. No single tool gives the final number, yet together they build a quiet, consistent case for heavy ongoing loss. A visual anchor steadies the page. See the star as a white furnace with a bright veil rushing outward, grain by grain like mist lifting from sunlit snow. In that lift, the future changes shape. The mass drops, the colour shifts, the end narrows toward a few likely paths rather than many. A final recap holds the thread line-driven wind, steel mass clumping and porosity set how the steeling reads, and gentle variability turns the theft into a breathing rhythm. Next comes the matter of neighbours and companions, because in a crowded cluster, a second star or a blended neighbour can masquerade as a single giant, and untangling that knot is essential for an honest measure. The early takeaway is that crowding and hidden companions can make a single beacon look impossibly massive, and careful untangling of neighbours restores honest brightness and steadier mass. The core of the R136 cluster is a tight city of newborn stars. In such a city, many points of light overlap within a single blurred patch. Blended light is the sum from several sources that arrive as one. When a blend is mistaken for a lone star, the assigned luminosity rises, and the inferred mass climbs with it. This matters because the title most massive can belong to an illusion if neighbours hide inside the glare. A small payoff arrives quickly. When sharpness improves and several contributors are separated, the light assigned to each drops to a truer value and masses follow suit. The mind can picture a street of candles seen through frosted glass. The cluster looks like one bonfire, but as the glass clears, the bonfire resolves into many flames, bright yet distinct. Adaptive optics helps ground telescopes push through the distortions of air by bending mirrors in real time. Space telescopes rise above air entirely, letting starlight form tight, clean points on the detector. Interferometry links telescopes into a larger virtual mirror, boosting the ability to separate close companions. Each of these advances pulls a hidden neighbour out of the glare, which is the direct route to reduced extremes and increased confidence. Companions also reveal themselves through motion. In a binary system, both stars orbit a shared centre. Their light shifts in colour as they approach and recede, and repeated spectra trace this rhythm. Radial velocity is the speed toward or away from the observer, read from the shift of spectral lines. Photometry watches brightness over time. If one star crosses in front of the other, the combined light dips in a tidy pattern. Eclipses, when present, pin down sizes and inclinations and transform a hazy guess into a stiff measurement. The payoff can be decisive. A bright source that once seemed singular becomes a pair with calculable masses, grounded by gravity and time more than by models. A calm recap helps sharper images split peaks, repeating spectra, find orbits, and light curves catch eclipses together, shrinking uncertainty and curbing overstatement. There is a quieter complication. Composite spectra occur when multiple stars contribute to one recorded rainbow. broadening and blending the lines. Composite light is not a single message but overlapping messages. Disentangling techniques separate those messages by tracking how features shift over weeks and months. As patterns part, one component may prove cooler, another hotter, and the combined brightness recalibrates to a fair share for each. This distinction matters because a composite that masquerades as an unusually hot giant can instead be two ordinary hot stars aligned. Visualize two singers holding a steady note, their voices close enough to seem like one. With patience, the ear learns the slight beating between them, and the single tone splits into two clear lines. Crowding also raises the chance of close passages and even mergers. A merger is when two stars join into one. In a dense cluster, gravitational nudges shuffle orbits and can funnel young stars into contact. Such events may briefly produce a genuinely larger single star than standard quiet growth would allow. If R136a1 formed through a sequence of close interactions or a union, the end result can still be a single object today, but its measured light must not be inflated by lingering neighbors. The gentle lesson is that both stories can be true. A real heavyweight can exist, and at the same time a portion of its claimed light can belong to others. Another payoff settles in. When these pathways are acknowledged, the record holder shifts from a brag to a boundary line drawn with a pencil rather than a marker. Distinguishing chance alignment from physical companionship is another task. Chance alignment places unrelated stars along the same line of sight. Physical companionship binds stars with shared motion and distance. In practice, proper motions and repeated high-resolution imaging reveal whether 2 points drift together or apart. In such a distant galaxy, motions are small, yet years of patient frames can show tiny relative shifts. If 2 points share a slow dance, companionship is likely. If not, alignment is the better answer. This matters because a bright peak with an unrelated foreground partner should never count the partner's light when weighing the target. A gentle recap lands blends mimic monsters. Companions can be weighed, mergers can occur, and only careful separation yields a trustworthy mass. Instruments supply the means. The Hubble Space Telescope delivers stable long-term imaging that tracks subtle change. The James Webb Space Telescope reaches into dustier wavelengths and resolves warm structures that used to smear together. The Very Large Telescope with adaptive optics engaged presses to tiny angular scales from the ground. Integral field spectrographs gather a spectrum at every point in a small field, producing a cube of data that maps light and color across the blur. With these tools, astronomers can both map brightness and measure motion at once, which is exactly what a crowded scene demands. A visual anchor steadies the thought. Imagine a ballroom filled with dancers seen from a balcony through shimmering air. At first, the floor is a blur of silver. Then the air steadies the pairs separate, and the choreography emerges as distinct figures moving with patterned grace. Once the figures stand apart, counting them and timing them becomes simple. In the same way, once the peaks separate, the claim of a single colossal dancer fades, replaced by a credible census of strong, bright partners. Finally comes meaning. Untangling companions does more than correct a number. It sets a firm baseline for theories that predict upper mass limits, clarifies how feedback from a cluster is apportioned among its bright members, and sharpens the link between individual lives and collective evolution. This matters because models of how the first generations of galaxies lit up depend on how often and how extremely giants can form. A last recap keeps the page calm. Resolution splits, blends dynamics, confirm pairs, an honest apportioning of light trims, exaggerated masses without erasing the rarity of true heavyweights. Next comes a compressed timeline, where even a paired-back giant rushes through burning stages in short order, writing a fast biography that will guide the forecast of possible endings. The early takeaway is that a very massive star lives fast, burns fiercely, and races through evolution on a timescale that feels like a brief flash, yet each step follows clear, steady rules. A star this heavy forms quickly because gravity has ample material and the crowded nursery keeps gas flowing inward. Once formed, it shines with daunting power, and that power drives a wind that begins trimming the outer layers from the first bright moment onward. The life, therefore, unfolds as a paired story of burning and peeling. Burning is the fusion of light elements into heavier ones. Fusion releases energy that provides the pressure, supporting the star against collapse. Peeling is the steady wind that carries surface gas away. Together they set the clock. A small payoff appears here. When both processes strengthen, change runs faster, and 1,000,000 years can hold a full biography. The first act is core hydrogen burning. Hydrogen burning means 4 hydrogen nuclei fuse into helium, releasing light and heat. In very massive stars, central temperatures climb until another route called the carbon-nitrogen-oxygen cycle dominates. The carbon-nitrogen-oxygen cycle uses those elements as catalysts to speed hydrogen burning. The detail matters because a faster route supports higher luminosity. Visualize a furnace under a bellows that never rests. The fire roars and the heat drives a constant outward flood. The core remains nearly convective, meaning hot material rises and cooler material sinks, mixing fuel and prolonging this stage. In calm terms, mixing stretches the first act while the wind gently shortens the outer layers. A recap settles: the core burns hydrogen efficiently, the envelope sheds, and the star stays blindingly bright. When core hydrogen nears exhaustion, the core contracts and heats. Contraction increases temperature and density. The envelope responds by swelling and changing colour slightly, although in the most massive cases the surface can stay hot, because the wind has already stripped many outer layers. Core helium burning follows. Helium burning fuses 3 helium nuclei into carbon, and sometimes carbon into oxygen. The energy is still strong, but the fuel runs out faster, because each step demands higher temperatures and yields less support time per unit mass. The clock speeds again. Imagine a flame turning from a broad, steady blaze into a series of hotter, tighter jets. The wind continues to peel and products of burning leak outward, changing the spectrum seen from far away. Lines of helium and nitrogen gain strength, and hydrogen features can change shape as mixing and loss rewrite the surface. A second payoff emerges. Observers can read these changes and place the star along its timeline even if the exact total mass remains uncertain. The third act includes brief stages of heavier element burning. Carbon burning creates neon and sodium. Neon burning yields oxygen and magnesium. Oxygen burning synthesizes silicon and sulfur. Silicon burning builds an onion-like structure with layers of different elements stacked around the core. Each step demands higher heat, supports itself for shorter intervals, and unfolds more quickly than the previous one. Definitions stay small. Carbon burning means carbon nuclei fuse into heavier nuclei. Neon burning means neon nuclei transform under extreme heat. The string of acts matters because it closes doors rapidly. Once a layer finishes its fuel, support shifts inward, and the path narrows toward a compact hot center. Picture nested shells glowing at different colors, all feeding the final core with energy while the outer skin keeps thinning in the wind. A calm recap helps: the sequence compresses the shell stack, and the wind keeps molding the silhouette. Timescales shrink as the star climbs the burning ladder. Hydrogen burning can last hundreds of thousands of years for such a giant. Helium burning lasts a fraction of that. Carbon burns in far less time, and silicon burns in an eye blink compared to the opening act. The contrast shapes a simple mental model. The story begins with a wide river narrows into a focused channel and finishes in a rapid cascade. The river image matters because it shows how overwhelming change becomes near the end without needing technical figures. Another thread is rotation. Rotation is the spin of the star around its axis. If rotation is significant, mixing increases, which can keep the surface hot and smooth and bring fresh fuel inward and processed material outward. Rotation, therefore, can lengthen early stages while raising mass loss through winds launched near the equator. The wind shape becomes slightly flattened, like a skirt of steam spread wider along the middle. This nuance matters because it changes how quickly the star uncovers its inner products and how it lights the surrounding nebula. Magnetic fields may also act as rails for the wind, guiding streams into preferred paths and adding to the patchy texture seen in spectra and images. A small payoff returns here. Even with these twists, the overall arc stays gentle and firm, faster, burning inside, steady, peeling outside, and a shortening road toward a compact core. The environment threads through everything. Fewer heavy elements in the Large Magellanic Cloud may soften the wind slightly, compared to a similar star in the Milky Way, which in turn can allow a higher birth mass and a slightly different surface at a given age. Yet the core still progresses through the same sequence, because fusion cares mainly about temperature and density. The lesson is comforting. Context adjusts the pace, but the script remains the same. A visual anchor quiets the page. Imagine a white furnace inside a luminous cavern. Close to the furnace layers glow like delicate glass bowls set one inside another, each bowl thinner than the last. Around the bowls, a continuous draft lifts fine grains into a slow, outward snowfall. The bowls warm and fade in turn, and the snowfall keeps drifting, shaping the cavern beyond. A final recap holds the thread: rapid burning stages, steady wind, layered shells, and a clock that moves from wide to narrow. Meaning follows. A short life still seeds a wide influence, because each stage plants different elements into the wind and sculpts new pockets for future stars. That is why the biography of a single giant matters for the long story of galaxies. Next comes a closer look at the core itself, where extreme temperature and pressure set the pathways of fusion and fix which elements appear first in that layered luminous onion. The early takeaway is that the core of R136a1 is a compact furnace, where heat, pressure, and simple reactions arranged in careful steps build heavier elements and set the star's remaining lifetime. A core is the central region where fusion releases energy. Fusion is the joining of light nuclei into heavier ones. Pressure is the inward squeeze from upper layers. In these depths, temperature rises to hundreds of millions of degrees, and particles move so fast that they can overcome their mutual repulsion and lock together. The first sustained chapter remains hydrogen fusion, but inside such a massive star it proceeds mainly through the carbon-nitrogen-oxygen cycle, which is a catalytic pathway that uses those elements to speed the fusion of hydrogen into helium. A catalyst is a helper that participates but is not consumed. The reason this matters is that a faster route supports a higher luminosity and a vigorous wind which ties core physics to the surface behavior. A visual anchor steadies the idea. Picture a circular workshop with 3 tools that pass small beads to each other, and with each pass a tiny spark pops free. The sparks add up to a steady blaze, and the tools complete the circle again and again. Helium accumulates in the center as hydrogen is consumed. When the central hydrogen drops below a threshold, the core contracts, because pressure from fusion declines. Contraction raises temperature and density, and a new steady chapter begins helium fusion. Helium fusion, also called the triple alpha process, turns 3 helium nuclei into carbon, and with enough heat some of that carbon fuses into oxygen. Heat supports the star again, and the core settles into a new balance, while hydrogen can continue to burn in a shell around the helium core. This shell structure is important. A burning shell is a thin region where a previous fuel continues to fuse around a core that has moved on. The consequence is layered work. The star produces energy both at its center and in a surrounding ring, strengthening the overall output while the wind continues to peel the outer layers. A calm recap lands. Hydrogen fuses through a catalytic circle. Helium takes over when contraction raises heat, and a shell carries the earlier work around the core. Mixing adds another strand. In very massive stars, rotation and buoyancy can stir deep layers. Mixing is the movement of material that brings fresh fuel inward and carries newly made elements outward. Because of mixing, the line between core and shell blurs a little, which stretches the duration of a stage and smooths changes at the surface. The gentle lesson is that the core is not a locked box but a busy kitchen where ladles cross the counter. With helium burning underway, the interior temperatures rise toward the thresholds for heavier fusion. Carbon burning occurs when carbon nuclei collide and build neon and sodium. Neon burning follows producing oxygen and magnesium. Oxygen burning proceeds to silicon and sulfur. Silicon burning is the last and fastest major stage before the end, assembling a layered interior like an onion. An onion structure means shells of different compositions stacked in order: hydrogen, outside, then helium, then carbon, then oxygen, and so on, down to a growing core rich in iron-like products. Iron-like means nuclei that do not yield net energy when fused. This is the quiet turning point of the entire story, because fusion beyond that point ceases to be a source of support. A small payoff arrives here. The concept stays simple as long as fusing yields energy. The star holds itself up. When fusion can no longer pay the pressure bill, the support fails. The core, therefore, is both engine and clock. Each new fuel demands higher heat and gives less time, so the ladder of stages shortens rapidly. Hydrogen burning may last hundreds of thousands of years for a giant. Helium burning lasts far less. Carbon burns for far less time again, and silicon burns for only days or less. A second recap helps. The staircase is steep, the steps become shorter, and each step tightens the inward squeeze. Electrons and radiation pressure also take part. Electron pressure is the push from electrons packed tightly together. Radiation pressure is the push from trapped light scattering many times before escape. Together they share the burden with thermal pressure while fusion continues. The balance is delicate but robust. Whenever cooling threatens to slow fusion, the core contracts and heats and fusion rises again. This self-regulating dance keeps the engine steady until fuel changes force a new act. Visualize a heavy pot on a tripod over a roaring fire. If the flame falters, the pot sinks, and the flame brightens as air flows faster under the rim. The system supports itself with quiet adjustments. Neutrinos thread through the story as deep, invisible messengers. A neutrino is a nearly massless particle that rarely interacts with matter. During the hottest burning stages, neutrinos carry energy from the core directly into space. Because they slip through the star without pause, they provide an energy loss channel that cooling gas cannot block. This matters because neutrino cooling shortens late stages and helps set the timing of the final approach. A third recap lands: fusion heats, mixing feeds, pressure adjusts, and neutrinos quietly drain energy so that late steps rush by. The surface listens to the core. As fresh layers rise, spectral lines shift in strength, revealing helium and nitrogen at visible depths and hinting at deeper carbon and oxygen. The wind remains the courier carrying products outward into the nebula where future stars will harvest them. This coupling between interior and environment is the thread that turns a single life into a communal legacy. Meaning rests here. The core does not only power the present glow, it writes the chemical future of its neighborhood. A visual anchor returns to the onion. Imagine translucent bowls stacked tightly, each lit from below their rims, trembling with heat. In the bowls, grains change color as they cook from pale to amber to deep red, and a fine steam rises steadily into the surrounding chamber. That steam is the wind, and it carries the taste of each bowl into the room. The final soft truth is straightforward. The core's path is a sequence of stable, comprehensible steps, each one supported by clear rules about temperature, pressure, and composition. Those steps, not dramatic surprises, shape both the clock and the fate. Next comes the outward effect of that furnace on its surroundings, where light and wind sculpt gas into shells and filaments, laying the groundwork for the next generation of stars even as this one races on. The early takeaway is that the light and wind from R136a1 do not stop at the star's edge, but sweep the surrounding cloud, shaping shells, filaments and cavities that both encourage and suppress new stars, turning one fierce life into a quiet architect of its neighborhood. Feedback is the loop where a star changes the gas that makes future stars. In the Tarantula Nebula, radiation carves out a clear cavity, while winds press a moving shock front into the denser walls. A shock front is a narrow region where compression runs ahead of the gas like a cresting wave. As the front advances, it squeezes knots along the rim, and each knot can tip into collapse if gravity overcomes pressure. Imagine a bright lantern inside a fine mist. The beam sculpts a hollow and piles moisture along a glowing rim, and on that rim beads form and fall. This matters because it sets the pace and place of the next generation. The rim brightens along ridges where ultraviolet light strips electrons from hydrogen. Ionized hydrogen gas glows, revealing where energy lands hardest and where dense pockets stand against the push. Yet light is not only a sculptor, it is also a broom. In low-density corridors, radiation sweeps material away and leaves channels too sparse to collapse. The wind joins the work. A line-driven wind streams outward and rams the wall of the cavity. Where it meets resistance, it slows and piles up a thin shell. Where the wall is weak, it punches through and fans into the larger cloud. The shell stores momentum and crumples into fingers and pillars, each one a potential nursery if the internal gravity is strong enough. A small payoff arrives here. The same force that clears a path also gathers material into promising seeds, making the nebula both a cradle and a keeper. Turbulence threads through every scene. Turbulence is the swirled, disorderly motion that breaks a flow into eddies. In the Tarantula Nebula, turbulence arises from overlapping winds from past eruptions, and from the cluster's own movement through the cloud. Turbulence matters because it creates a spectrum of clump sizes, and clumps of the right mass and size can resist erosion long enough to collapse. Visualize foam on a tide flow where some bubbles pop at once while others gather into sturdy rafts that drift to calmer water. At the same time, radiation can heat and thin the outer layers of a clump, delaying its fall inward. The outcome depends on balance. Push too hard, and the clump disperses. Push just enough, and the clump tightens. A calm recap settles the picture. Radiation hollows and lights the cavity. Winds drive shells and fingers, and turbulence selects which knots endure to become stars. Dust adds tender detail. Dust grains are tiny solids mixed with gas. They absorb energetic light and glow in the infrared, outlining the filaments that crisscross the cavity walls. In places where dust gathers, it shields gas beneath from the strongest glare, creating cool pockets where molecules survive. Molecules are bonded groups of atoms. Within these pockets, chemistry proceeds, and carbon-based chains and simple molecules signal that the raw stock for future planets has survived the storm. This survival matters because massive stars do not simply erase what surrounds them. They also prepare a textured landscape where variety can thrive. The Very Large Telescope and space observatories confirm these contrasts. Images show arcs that match wind-blown shells, and spectra reveal speeds that fit outward flows. The James Webb Space Telescope traces warm dust along the same arcs and finds bright knots in the rims where compression peaks. No single frame tells the whole story, but together the shapes and motions reveal a consistent pattern. Energy flows out matter, gathers at boundaries and collapse. Cautiously begins where that gathering is slow and strong. A second payoff lands. The environment becomes legible, less a chaotic glow and more a map with cause and effect. Feedback also limits how large new stars can grow. In the cavity's center, the combination of strong light and fast wind strips would be embryos before they can gather much gas. Farther out beyond the sharpest glare, conditions soften and allow a wider range of masses. This gradient sets a quiet order very close to the giants. Small stars dominate. At the rim, a mix appears. In the darker lanes beyond, larger embryos can strive. That order matters because it ties the mass distribution of newborn stars to distance from the brightest sources. The neighborhood, therefore, contains an imprint of its brightest member's life. A gentle recap helps near is harsh and limiting. Midway is mixed and productive. Far is calmer and more permissive. The cavity itself grows with time, but not uniformly. It expands fastest where the wall is thin and slows where dense knots hold. As the shape becomes lopsided, fresh fronts cut new paths, and the overall structure develops chimneys and arches. Visualize a honeycomb with openings melted wider by a steady flame, while other cells resist and keep their hexagon ribs. These forms matter because they act as vents for future explosions and as channels for the escape of hot gas. They also set where ionized regions will later meet cold gas, which is the border where the next bright rims light up. Light echoes at a human pace when fronts sweep a ridge over tens of thousands of years, a blink in the life of a massive star, yet a long season in the cloud. Meaning emerges quietly from this choreography. A single giant can appear destructive, yet the pattern of destruction and creation is balanced. By carving a cavity, this star prevents runaway collapse nearby that would have made an unruly swarm. By compressing rims, it prompts organized pockets that can grow with less interference. By heating dust and forging molecules, it seeds chemistry that later worlds will inherit. The neighborhood becomes a garden shaped by both pruning and planting. A visual anchor steadies the mind. See an illuminated cavern whose walls glimmer with beads strung along ridges, each bead a small cradle, while a clear floor circles a central fire. Wisps drift gently upward along carved columns, and in the columns the seeds of future lights rest in shadow, waiting for the glare to fade. A final recap holds the thread radiation clears and light's winds press, and gather turbulence selects dust shelters and remembers, and together these forces write the blueprint of what comes next. That blueprint also narrows the likely endings of the present giant because the surrounding density, the rate of loss, and the energy escaping now will all influence the kind of finale that follows. Next comes a measured survey of those ending from brilliant explosions to deep, quiet collapses, and how probabilities shift for a heavyweight born in this luminous, crowded cradle. The early takeaway is that a very massive star like R136a1 faces only a few endings, and each ending follows quiet rules that depend on mass rotation, wind loss, and the chemistry of its birthplace. An ending here means the way the core finally fails or transforms. The possibilities include a classic core collapse supernova with a remnant, a pair instability route that partly or wholly unbinds the star, or a direct fall into a black hole with little light. The reason this matters is simple. The ending sets which elements are released, how much energy shakes the nebula, and what compact object remains to influence the cluster. A calm path begins with core collapse. Core collapse happens when the inner core becomes rich in iron-like products that no longer provide fusion support. Without new energy, pressure loses ground and gravity wins inward. The core falls, densities soar, and a central object forms that can be a neutron star or a black hole depending on mass. A shock forms and struggles against infalling layers. If the shock revives energy and neutrinos drive an explosion that throws the envelope outward, the remnant then sits in the cavity, and the ejected layers mix with the nebula. This route is familiar across many massive stars, but its strength and brightness vary with how much mass remained at the end. A small payoff arrives. If winds have already removed much of the envelope, the blast and the light curve look different than a thickly wrapped star. The next possibility invokes a more delicate instability. Pair instability arises when photons in the hottest layers convert into particle pairs, draining pressure that light once provided. When pressure falls, parts of the star contract and heat. The heating can ignite oxygen violently, which can either pulse the star or unbind it completely. A pulsational pair instability event ejects large shells in several waves, while the core may survive to collapse later. A full pair instability supernova disrupts the star entirely, leaving no remnant. The difference hinges on the mass of the inner layers at the time of instability. This path matters because it changes both the timeline and the signature in the surrounding cloud. Pulses build shells at set distances, and a later collapse can light those shells into layered echoes. A gentle recap helps. Core collapse keeps a compact object, and sometimes a strong flash pulsational pair instability makes several sheds before a final fall, and full pair instability leaves only an expanding memory. There is a third road that can be the quietest. Direct collapse means the star falls inward and crosses the threshold for a black hole without a strong outward shock. In such a case, much of the envelope follows the core and the light is modest compared to a classic explosion. The final product is a black hole, and the environment sees less fresh enrichment. This ending matters because it rewrites expectations for chemical yields in a young cluster, and it changes how feedback unfolds in later generations. Which road is most likely for R136a1 depends on present mass, the mass still to be lost in winds, the composition that controls opacity, and any rotation that stirs and supports the inner layers. Fewer heavy elements in the Large Magellanic Cloud tend to lessen line-driven winds, compared to the Milky Way, which can leave more mass at the end. More mass at the end nudges probabilities toward either pair instability thresholds or direct collapse. Yet strong winds and mixing can still trim the star enough to keep it below full pair instability. Rotation can lengthen, burning stages alter how the core grows, and distribute angular momentum into the envelope. If rotation remains high, a collapsing core may form a disk that feeds a jet, shaping the light if a breakout occurs. However, the crowded environment can also sap rotation through interactions. The balance of these gentle influences sets the likely path. A small payoff returns. Even with uncertainty, the menu narrows to a few endings guided by measured factors, not by surprise. Observers look for clues in the present wind, the surface composition, and the cluster's structure. A surface rich in helium and nitrogen points to deep mixing and advanced peeling, which supports a scenario where the envelope is thin by the end. Thin wraps favour faster shock breakout and distinctive light curves if a collapse becomes explosive. Thick wraps favour slower emergence or more absorption of energy. Meanwhile, arcs and shells in the nebula can betray earlier pulses, especially if they align with expected speeds from pulsational events. The absence of such rings does not rule pulses out, but it tilts the scales toward a simpler shutoff. A calm recap lands. Composition hints at the stage winds measure the peel, and structures reveal past breaths together, sketching the forecast. Meaning steps out softly. An ending that leaves a black hole adds a heavy point mass to the cluster core. That object can later partner with a neighbour and spiral together, eventually emitting waves that pass through space like ripples in a dark pond. An ending that disrupts the star spreads oxygen, magnesium, silicon, and heavier products into the walls of the cavity, enriching the next generation. A pulsational path can shape the nebula with concentric shells that later stars inherit as sculpted lanes. Each outcome writes a distinct signature into the shared environment. A visual anchor steadies the thought. Picture a luminous bell that has rung for a short season. If it shatters in a bright final strike, shards seed the floor with sparkling grains. If it sighs and folds inward, it leaves a quiet, dense weight at the centre. If it rings in a series of deep pulses, it carves circles in the dust before the last note fades. The star's present mass is the quiet switch that selects the bell's last tone. Uncertainty remains honest. Crowding still complicates brightness. Wind clumping still blurs loss rates, and rotation is not perfectly known. Yet the trend is steady. As images sharpen and models include lower heavy element content, and wind porosity forecasts converge on a narrow band of possibilities. In essence, the giant will end either by a collapse that leaves a compact remnant, perhaps with modest light, or by a layered sequence of pulses, followed by a collapse, or, less likely, by a full disruption, if enough mass persists at the key moment. A final recap keeps the page clear. The path to the end is set by present mass wind history composition and rotation. The signatures range from quiet collapse to layered pulses to a full unbinding. Next comes the question of what these endings forge and how those products travel from the core into the cloud, because the story of one short life reaches its widest meaning through the elements it builds and the places they settle. The early takeaway is that a very massive star forges a broad suite of elements in its core, and shells then spreads those products through winds, and later potentially through an ending burst. Element forging means nuclear fusion that assembles heavier nuclei from lighter ones. In the earliest, longer stage, hydrogen turns into helium through the carbon-nitrogen-oxygen cycle, which is a catalytic loop that accelerates fusion. The heat and light from this loop support the star and feed the wind that begins carrying traces of processed material outward. As hydrogen declines at the center, the core contracts and helium fusion begins building carbon and oxygen. A small payoff appears here. The transition from hydrogen to helium burning makes the first clear jump in chemical variety, and that jump already matters for any future planets in the neighborhood. Helium fusion forms carbon through the triple alpha pathway. Carbon then captures helium to make oxygen. In calm terms, the core becomes a workshop that locks 3 small beads into a triangle, then adds a 4th bead to grow a heavier figure. The wind driven by light carries hints of this work upward. Mixing brings helium and nitrogen to the surface, and later signs of carbon and oxygen appear. Each sign is read in lines stamped on the spectrum, the star's light split into colours, where each element leaves a subtle notch or glow. A recap helps: hydrogen yields helium, helium yields carbon and oxygen, and winds and mixing reveal this progress at the surface. As the core heats, further carbon burning begins. Carbon burning fuses carbon into neon, sodium and magnesium in energetic reactions. Neon burning then proceeds, turning neon into oxygen and magnesium through rearrangements under higher heat. Oxygen burning follows, building silicon and sulfur. Silicon burning is the swiftest and hottest of the late stages. In that stage, a complex network moves particles among nuclei, climbing toward a center, rich in iron-like products. Iron-like means nuclei that do not release net energy when fused. The onion structure forms naturally, with shells of different fusion burning stacked above the core. Hydrogen burns in a shell outside helium. Helium burns in a shell outside carbon. Farther inward, nested shells glow in sequence as heavier fuels kindle. This layered design matters because each shell releases energy and supplies products to the region above it. A second payoff arrives. The wind and any later outburst inherit a menu of elements already prepared at distinct depths, so the final distribution can be traced back to the onion's layers. The local environment shapes the details. Fewer heavy elements in the large Magellanic Cloud slightly change opacities and wind strengths. Lower opacity softens the outward push, which can allow more mass to remain longer and change how deeply the wind bites. Yet the fusion ladder stays the same, since temperature and density set the rules. The product list therefore remains familiar. Carbon, nitrogen and oxygen appear early. Neon, sodium and magnesium follow. Silicon and sulfur rise in later stages, and iron-like groups accumulate in the heart. A gentle recap lands: the path of elements is universal. The pace is tuned by environment, and the wind is the courier. Dust formation is another thread. Dust is solid grains built from available elements in cooling gas. In the immediate wind of a very hot star, dust formation is limited, yet in shocked regions where winds collide with surrounding gas, temperatures can drop enough for grains to form. Carbon-rich grains and silicate grains can condense in those cooled pockets. These solids matter because they shield molecules, catalyze chemistry, and help future clouds clump. They become seeds that later planetary systems can inherit. A visual anchor steadies the page. Imagine a glowing kiln that shapes not pots but powders, and outside the kiln a breeze collects those powders into fine floating seeds that settle along ridges of the cavern. The star's ending selects how the forged stock spreads. If core collapse launches, a strong shock shells of the onion can be torn apart and elements cast across the cavity. In that case, oxygen, magnesium, silicon and sulfur fill the walls, and iron group products may also escape depending on how the shock moves through the core. If the end is a direct collapse, the spread is gentler during the final moment, and much of the innermost product falls inward. Even then, the long prior wind has already salted the nebula with helium, nitrogen, carbon and oxygen. If pulsational pair instability pulses occur, layered shells leave their signature at measured distances, ready to be lit later by a final flash. A small payoff returns. The nebula itself becomes a memory map of the star's inner layers, arranged by distance and speed, readable for a time in arcs and knots. The meaning broadens quietly. Every rock ice grain and future ocean draws on elements whose first abundant sources were massive stars like this one. Carbon frames organic chemistry. Oxygen binds with hydrogen to make water. Magnesium and silicon build the backbone of rocky minerals. Iron sets the character of planetary cores. Nitrogen enriches atmospheres and chemical cycles. These connections are not abstract. They are the tangible bridge from a brief hot life to the patient surfaces of future worlds. A recap keeps the rhythm, fusion builds, the table wins and endings set. The delivery and clouds inherit the stock. Observations back this chain. Spectra of the Tarantula Nebula show bright oxygen and sulfur lines in the walls of the cavity. Infrared maps reveal warm dust consistent with silicate and carbon-rich grains close to active fronts. Kinematic data trace outward flows whose speeds match expected wind and shock interactions from massive stars. Patterns align without needing any dramatic leaps. The elements appear where compression and cooling invite them to gather, and the momentum lines up with the known energy sources in the cluster. This alignment matters because it turns a glowing panorama into an understandable ledger of inputs and outputs. A final visual anchor lingers. Picture shelves in the caverns stacked with bowls labelled with simple names: carbon, oxygen, magnesium, silicon, sulfur, iron. A steady hand lifts powders from the bowls and lets them drift into the open air, where gentle draughts carry them into folds of the wall. In time, those folds darken into seeds of new clouds. The last recap holds the thread, the core creates a sequence of elements, the shells arrange them, the wind and any final act disperse them, and the nebula writes them into future stars and worlds. Next comes a wider lens that compares this luminous nursery to ancient starburst regions, showing how one nearby furnace becomes a guide to the distant youth of galaxies. The early takeaway is that the Tarantula Nebula around R136a1 mirrors the intense star-forming regions of the early universe. So studying this nearby furnace clarifies how young galaxies first lit the cosmos. A starburst is a period when a galaxy forms stars at a very high rate. In the first billion years, many galaxies likely lived through such bursts under low heavy element conditions. The Large Magellanic Cloud hosting the Tarantula Nebula has fewer heavy elements than the Milky Way, so it provides a closer match to that ancient chemistry. This similarity matters because the recipe of a cloud changes how bright its stars become, how strong their winds are, and how quickly gas transforms into new generations. Visualize a laboratory bench placed beside a window into the past. The bench holds real instruments and local targets, while the window frames distant red-shifted galaxies whose light left before the present-day dust formed. By comparing the bench and the view patterns line up, a small payoff arrives here. When spectra from the Tarantula Nebula match features seen in young galaxies, confidence grows that the same physical rules are at work across vast times. In early galaxies, giant clusters likely crowded just as R136 crowds, and radiation carved cavities that regulated further birth. The balance between push from light and pull from gravity set the same ceilings on stellar mass, though details varied with metal content. The Tarantula Nebula shows how feedback sculpts shells and filaments, and how turbulence selects which clumps endure. Those same forms appear scaled up in starburst cores where thousands of massive stars overlap their spheres of influence. A calm recap helps. Nearby, the Tarantula Nebula supplies detail. Far away, primeval galaxies supply context. Together they tell one story about how stars gather and how they limit themselves. Dust is central to this bridge. In the early universe, dust had fewer heavy elements to build, with yet supernovae and winds from massive stars quickly seeded grains. In the Tarantula Nebula, dust outlines bright rims and cooler pockets that protect molecules. The same role likely played out in young galaxies where the first dust-sheltered chemistry that later built complex organics. This matters because dust sets the visibility of early light and alters the temperature of the gas. When dust is sparse, radiation escapes more easily, boosting the reach of ionizing light that creates larger glowing regions. When dust thickens, pockets survive and later collapse. A second small payoff appears. The Tarantula Nebula demonstrates both regimes side by side, clear channels and shielded folds, giving a living map for interpreting the mixed signals from early galaxies. Element making also connects near and far. The forging of carbon, oxygen, magnesium and silicon in giants like R136a1 feeds the raw stock for later stars and planets. In the young universe, that forging began quickly because massive stars lived short lives and returned products to their clouds. The Tarantula Nebula's shells and filaments echo that cycle in miniature. Observed lines of oxygen and sulfur in the rims and dust signatures around warm arcs match the expectations for regions where recent massive stars have shaped the medium. These echoes give a quiet confidence that distant line ratios in early galaxies trace similar processes. A gentle recap lands. Chemistry, dust and radiation in the Tarantula Nebula become a Rosetta Stone for reading ancient faint signals. The role of clustering adds another layer. In early eras, clusters grew large and dense, favouring dynamical interactions and possible mergers among young stars. The R136 core offers a nearby case where crowding companions and blends complicate mass estimates, but also open channels for unusual growth paths. If mergers occasionally produce genuine heavyweights, early starbursts would have hosted them more often, reinforcing the need to interpret extreme light with caution. The lesson is comforting. Even in intense settings, the same careful steps of resolution, spectroscopy and dynamics can sort the crowd into credible members and revise exaggerated claims. Visualize a distant city at night seen through humid air, its skyline smeared into a single glow. The Tarantula Nebula is the stroll within the city, where streets and windows can be counted, and where signs on doors match the tones of the distant blur. Matching labels to blur is what turns a luminous smear into a census of stars' shells and flows. Star formation efficiency also rides this bridge. Efficiency means how quickly gas turns into stars. In early galaxies, strong feedback may have limited efficiency in the core while fostering organized growth at edges. The Tarantula Nebula shows that pattern at smaller scale with suppression near the brightest sources and ripened pockets along the cavity rim. This gradient matters because it shapes the mass distribution of newborn stars, and therefore the total light budget delivered by a starburst. A calm recap keeps time. Less metal content raises potential birth masses slightly. Feedback sculpts, cavities, edges nurture a spectrum of stars and winds, and radiation regulate the pace. Instruments draw the connection tighter. The Hubble Space Telescope measures crowding and reveals the tight core of R136. The James Webb Space Telescope maps dust and molecules that trace sheltered pockets. Ground-based arrays with adaptive optics and integral field spectrographs connect motion and chemistry across small scales. Each capability has a partner in the study of distant galaxies, where similar data arrives smeared by distance and time. By establishing templates nearby, astronomers decode the far faint scenes with fewer leaps. A third payoff arrives. The more exact the local blueprint, the calmer the interpretation of ancient light. Meaning follows quietly. R136a1 is not only a local curiosity, it is a guidepost for an epoch when galaxies were young and loud with fresh stars. Its winds, its possible companions, its environmental setting, and its likely ending all stand in for the many giants that lit and shaped the first bright periods. Understanding its limits teaches the limits of the early universe's fireworks, and understanding its gifts clarifies where the first stable clouds for long-lived stars could grow. A visual anchor steadies the thought. See a bright hearth in a stone hall. The hall is the young universe, the hearth is a cluster like R136, and the smoke that curls to the rafters is the light and dust that escape to warm, distant corners. The same fire dries some floors and moistens others, leaving patterns that later builders follow. A final recap holds the thread. Nearby detail sets distant context chemistry, and dust connect eras, and clustering explains extremes. Next comes the quiet triumph of tools themselves, because clearer instruments and longer patience have turned a crowed knot into a readable page, and those same tools continue to refine what is truly known about this luminous giant. The early takeaway is that clearer instruments and steadier methods turn a crowded knot of light into a readable page, so the picture of R136a1 becomes calmer, more precise, and more trustworthy with each technological step. The Hubble Space Telescope stabilizes long looks above the atmosphere and delivers sharp, repeatable images that anchor measurements over years. The James Webb Space Telescope reaches into the infrared where dust glows and where glare softens, revealing warm structures and hidden companions behind bright veils. The Very Large Telescope uses adaptive optics from the ground to cancel the blur of air in real time, bringing star images toward their crisp, natural shapes. Adaptive optics is a technique that reshapes a mirror to counter atmospheric distortion. This matters because once blur subsides, a single bright peak can split into several members, and mass estimates that once relied on a blended brightness settle into fairer shares. A small payoff arrives quickly. When a suspected monster resolves into multiple luminous but ordinary giants, the claim grows modest, and confidence grows strong. Spectroscopy takes the next turn. A spectrograph spreads starlight into a rainbow of finely spaced colours. In that rainbow, lines shift and broaden in ways that reveal temperature, surface gravity, wind speed, and composition. Radial velocity is speed toward or away from the observer read from line shifts. Surface gravity is weight at the surface read from how lines broaden and shape. When spectra are gathered repeatedly, motions betray companionship. Two stars that share an orbit imprint gentle alternating tugs on their lines. If an eclipse occurs, the combined light dips in a steady pattern. Photometry is the precise tracking of brightness over time. Eclipses are alignments where one body passes in front of another. Together, these readings move mass from a model-based estimate to a more geometric determination grounded in motion and time. And a calm recap helps sharper images assign light correctly. Spectra read heat and motion, and light curves reveal orbits, and all three combine to pull uncertainty inward. Integral field spectrographs add a valuable layer. An integral field spectrograph collects a small image at every wavelength in a narrow field, creating a three-dimensional cube of data. This cube stores color and position together, allowing astronomers to map wind features and subtle companions across the same patch where light once blended. In crowded cores like R136, this mapping matters because it ties a spectral fingerprint to a precise spot, avoiding the confusion that comes when two neighbors share similar colors but different motions. Interferometry pushes resolution even further by linking telescopes to act like a larger mirror. In the near-infrared, this technique can separate companions too close for single mirrors to resolve. Interferometry is the combination of light from multiple telescopes to improve resolving power. The reward is a finer separation of peaks and a more honest apportioning of brightness. A second payoff lands. With positions known and orbits sketched, any one object's brightness can no longer steal from its neighbor, and extreme claims soften into sustainable values. Space and ground work together. The Hubble Space Telescope tracks long-term changes in the core and provides a stable baseline. The James Webb Space Telescope traces warm dust and organic molecules, marking sheltered pockets and outlining how winds meet walls. The Very Large Telescope and other large mirrors deliver high-signal spectra and adaptive optics images that update more frequently and at a range of wavelengths. Radio arrays see the broader cloud and the shock fronts where winds and earlier eruptions meet, while future facilities promise even finer scales. Each platform has a specialty, and their overlaps fill gaps in a way that no single instrument can. A gentle recap lands space steadies and peers through. Dust ground sharpens and repeats quickly, and together they stitch a fuller portrait. Data handling is also a quiet hero. Crowded field photometry is a method that fits mathematical star images to packed scenes, extracting accurate brightness from overlapping points. Deconvolution is a technique that removes known blur from an image to restore detail. Disentangling is the spectral analog separating blended signals into component spectra by tracking how lines shift over time. These tools matter because they counter the exact problems that once inflated mass estimates in R136, overlap, glare, and motion too small to see by eye. Visualize a scribe restoring a palimpsest by gently lifting one script from beneath another. The page that seemed chaotic becomes a clear column of lines. Calibration keeps everything honest. Observers cross-check distances using well-measured markers in the Large Magellanic Cloud, apply dust maps that record how much dimming occurs across the Tarantula Nebula, and test their models against nearby clusters, where companionship and mass are already known from orbits. A small payoff returns here. Each corrected bias nudges the answer downward in drama and upward in reliability, and that trade is the quiet triumph of careful astronomy. Instruments also listen for signs of wind behavior that support the near-limit picture described earlier. Broad emission lines with specific shapes indicate fast outflows. Flickers that repeat suggest surface structures or gentle pulsations. Polarization, a subtle alignment of light waves, can betray a symmetry in the wind or a disk in a companion. None of these markers alone decides the mass, but they sketch a consistent backdrop for the idea that radiation pressure and line-driven outflows regulate the star. A calm recap keeps cadence lines speak of wind flickers of surface and polarization of shape, and together they align with the physics of a bright peeling giant. Visual anchors steady the mind. Imagine a busy night harbour seen first through a rain-smeared window, then through a cleaned pane, then from a balcony cleared of fog with a field glass that also breaks each lantern into its colour bands. Boats that once fused into a single glare separate, their wakes become singular, and their rhythms can be timed. The mental picture explains why claims cool as clarity rises. Meaning follows. The point of these tools is not to puncture wonder, but to place it where it can last. A star that remains extraordinary after the blur is removed is a stronger guide to the true limits of star formation than a legend sustained by glare. Measurements that agree across platforms strengthen the map that connects mass, wind, and fate. Templates drawn here will guide interpretations of distant young galaxies where detail is scarce, and patience must substitute for proximity. A final recap holds the thread. Improved sharpness, splits blends, repeated spectra and light curves reveal orbits, integral field cubes tie fingerprints to places, and careful calibration dampens exaggeration. Next comes the sober practice of revising the record because numbers for a champion do not stand still. They drift as evidence improves, and that drift is how science finds its calmest centre. The early takeaway is that revising the record is not a retreat, but the natural, careful motion of science toward truer numbers, so the portrait of R136a1 grows steadier as claims soften and converge. Early images of the cluster core gathered many bright sources into single peaks, and those peaks carried mass estimates that leaned high because blended light inflated brightness. As adaptive optics matured and space-based cameras sharpened those peaks, split into neighbours, and each neighbour received a fairer share of light. Luminosity estimates step down, and any mass derived from them step down with grace. A small payoff arrives quickly. The star remains enormous even after moderation, which means the lesson is preserved while exaggeration falls away. Spectral models have improved alongside images. Earlier grids used fewer chemical mixes, coarser wind clumping, and simpler treatments of line blanketing, which is how heavy elements absorb and reshape light. Newer grids fold in clumps, porosity, and lower heavy element content appropriate for the Large Magellanic Cloud, which changes the derived temperatures and gravities. Those changes in turn alter the inferred radii and luminosities. A calm recap helps sharper images fix the light better. Models fix the translation from light to power, and both together cool overheated estimates. Distance and dust corrections have also tightened. The distance to the Large Magellanic Cloud is now well pinned by multiple methods, and dust maps across the Tarantula Nebula have grown finer. Dust dims and reddens light. Using maps derived from many traces, observers correct each line of sight, rather than leaning on a single average. That precision matters because a small change in dimming creates a large change in derived power for a very bright star. When the correction is tuned to the exact path through the nebula, the uncertainty shrinks. A second payoff lands. Less scatter in the inputs yields less scatter in the mass. Dynamics add an anchor when companions exist. When a star shares an orbit, repeated spectra reveal a period and speeds that gravity turns into masses with fewer model assumptions. In the crowded heart of R136, orbits are hard to trace, yet patience reveals patterns more often than expected. Even non-eclipsing pairs can constrain mass ranges, and a confirmed companion inevitably steals some light from the target. Each detection trims the headline while strengthening the truth beneath it. A gentle recap settles the rhythm. Resolution divides light dynamics weigh it, and both conspire to rescue reality from glare. Community practice evolves too. Teams compare independent pipelines for crowded field photometry, exchange synthetic images to test recovery of known inputs, and post updated values with honest error bars that reflect both random noise and systematic uncertainty. Error bars are the stated range within which the true value likely lies. Honest ranges dignify a record more than a dramatic single number can. They allow two groups to agree in spirit while their best estimates differ by a reasonable margin. That culture matters because it keeps the discourse calm and cumulative. Visualize a ring of surveyors around a bright hill, each with a level and a stick. As they call out heights, the chorus converges not to a spike but to a plateau. Another strand is the recognition of how a label shapes thought. The phrase "most massive" invites a chase to top a number. The revised view favors upper envelope, the smooth curve that marks the practical ceiling set by physics and environment. In this view, R136a1 sits near that envelope, and the exact vertical height shifts slightly as tools improve. The value of the case lies in how well it defines the envelope's shape, rather than in how boldly it rises above neighbors. A small payoff returns. The question turns from who wears a crown to how stable the roofline really is. Instruments continue to feed this process. The Hubble Space Telescope maintains a long stable record of the core. The James Webb Space Telescope maps warm dust and highlights companions and structures that used to hide in glare. The Very Large Telescope with adaptive optics provides frequent high-resolution updates. Integral field spectrographs bind color and position together so that each spectral signature can be tied to a specific point. Interferometers resolve separations that once seemed impossible. Together, these tools make it hard for an illusion to survive more than a season. A calm recap keeps cadence time, baselines grow, wavelengths broaden, and techniques overlap and the net tightens. Numbers move in response. Where early estimates suggested extremely high initial masses, revisions bring them to slightly lower but still towering values that agree better with limits set by radiation pressure, wind theory, and observed stability. Where current mass once stood at extreme peaks, updated light shares and refined winds pull the figure toward a range that still tests models, but no longer strains them. That drift matters because theory and observation meet more comfortably on the same page. It is easier to explain a rare giant that skims the limits than a monster that ignores them. Visual anchors help. Imagine a sculpture emerging as a sculptor removes coarse clay added during a rough blockout. The figure that remains is strong and balanced with lines that match what the stone can support. That is the effect of revision here. The giant remains a giant, but its silhouette fits the physics that hold it together. Meaning unfolds naturally. A refined mass for R136a1 clarifies the cluster's total energy budget, the rate at which the cavity grows, the expected strength of the wind, and the likely set of endings. It strengthens comparisons with ancient starbursts by ensuring that templates do not oversell extremes to explain faint distant light. It also pulls theory toward tighter predictions for the upper mass function, the curve that describes how many stars form at each mass. The benefits collect even if the headline number steps down. A final recap holds the thread. Revision is progress, moderation is strength, and convergence is the quiet triumph of shared methods. Next comes the wide, gentle close that places this single life in a larger frame, drawing together limits, cycles, and perspective, so that the scene rests with clarity rather than noise. The early takeaway is that R136 as A1 teaches limits without removing wonder, showing how gravity, light, and environment together shape a rare life that still obeys simple, steady rules. The setting is the Tarantula Nebula inside the Large Magellanic Cloud, a crowded nursery whose density, turbulence, and strong radiation allow an extreme birth while guiding a calm unbuilding through winds. The star stands near the practical ceiling, where outward push from light and inward pull from mass nearly balance, so the surface peels in a regulated breeze rather than in sudden drama. This balance matters because it anchors the idea that even the greatest giants remain within a framework that observation and theory can share. A small payoff arrives quickly. Once blends with neighbours are separated and dust dimming is corrected, the mass remains enormous, yet modest enough to fit within the ridge drawn by radiation pressure and wind physics. A gentle recap sets the rhythm. Nurture and nature combine, brightness meets gravity at the ledge, and the wind writes the pace. The arc of the star's life is brief but structured. Hydrogen burning through the carbon-nitrogen-oxygen cycle supports the early blaze, while mixing carries fresh fuel inward and processed material outward. Helium burning follows and builds carbon and oxygen, and then brief stages climb to silicon and sulfur, while an onion of shells forms around a tightening core. Each rung shortens the clock. Neutrinos drain the hottest stages and the wind keeps thinning the outer layers so that the surface chemistry reflects progress within. The outcome is not chaotic. It is a sequence of steps that converge on a narrow set of endings, from a quiet collapse that leaves a black hole to layered pulses that shed shells to a rarer full disruption if the inner mass stays above a critical band. A second recap helps faster burning inside, steady peeling outside, and a forecast chosen by present mass wind history, composition, and rotation. The neighborhood carries the signature of this life. Radiation hollows a cavity, winds push shells and pillars, and turbulence selects which knots endure to become new stars. Dust grains glow along the rims, shielding molecules in cooler pockets, and preserving chemistry for future clouds. The same forces that prevent runaway collapse near the center gather material along the edges, so pruning and planting proceed together. This scene is a garden shaped by a bright hand, not a wasteland. This matters because it links a short, fierce life to a long, quiet future, where carbon, oxygen, magnesium, silicon, sulfur, and iron-like products seed the next generation. The picture improves as instruments and methods mature. The Hubble Space Telescope steadies the core above the air. The James Webb Space Telescope traces warm dust and reveals companions that hide behind glare. The Very Large Telescope and other large mirrors, guided by adaptive optics and integral field spectrographs, map light and motion in the same crowded patches. Interferometers resolve separations once thought unreachable. Crowded field photometry deconvolution and spectral disentangling pull clean signals from overlap. The effect is cumulative. Each refinement trims exaggeration and raises confidence, and the star becomes a trustworthy guide to what is truly possible, rather than a legend based on blur. A calm recap lands, clarity grows, claims cool, and understanding strengthens. The meaning reaches beyond this one cluster. The Large Magellanic Cloud's lower heavy element content provides a bridge to the early universe, where starbursts likely formed many hot massive stars in dense groups. Lessons learned here scale outward feedback regulates growth edges ripen, and extreme masses remain rare but real, bounded by the same balance of light, gravity, and opacity. Templates drawn from this nearby laboratory help decode redshifted galaxies whose details are blurred by distance and time. The benefit is not only conceptual, it is practical, because clearer local blueprints reduce the need for dramatic leaps when reading ancient light. A third recap keeps cadence near detail, far context, and one set of rules. Revision sits at the heart of the story. Early numbers leaned high because blends and simple models pushed in the same direction. Later numbers stepped down with better separation of sources, finer dust corrections, and improved treatment of wind clumping and porosity. The record does not shrink the star into comfort. It places the star where physics had quietly drawn a line all along. That placement is the quiet triumph of patient work. It keeps the object extraordinary and the explanation stable. It also shifts attention from a crown to a roofline, from the contest of superlatives to the contour of an upper envelope that theory and data can trace together. A visual anchor steadies the thought. Imagine a tall bell tower emerging from morning fog. At first, the silhouette looks impossibly high. As the fog thins, the tower reveals crisp stones and a height that still amazes, yet now rests neatly on foundations that fit the ground. That is the comfort of a moderated record. It lets awe and understanding share the same square. Finally comes perspective. R136a1 is one life short by galaxy standards and long by a human clock, but it threads through many stories at once. It demonstrates how a rare environment can lift birth mass, and how the same environment through light and wind immediately trims it back toward a stable frame. It forges elements that later worlds require, sculpts pathways for new stars, and by ending clear space or seeds, shells that will shape what follows. Science advances around it with tools that split blends and settle motion into orbits, with models that fold in clumps and porosity, and with a culture that values convergence more than noise. A final recap holds the thread limit's clarified cycles connected and wonder kept. The path ahead is gentle. With each season of images and spectra, the portrait will gain another line of detail, and the giant will remain a guide rather than a puzzle. Next comes a soft release into the wider stillness, where the busy cradle quiets, and the scene rests with the understanding that even the brightest flame belongs to a pattern that is calm at its core. The scene settles into a wide, gentle hush. The Tarantula Nebula breathes slowly, its carved walls faintly aglow, while the cavity holds a memory of bright seasons now passing into calmer weather. R136a1 continues to shine, but the mind now carries a simpler map. Gravity holds, light pushes, winds peel, and the environment receives and reshapes the flow. The story of layers and shells, of mixing and measured loss of companions, and careful instruments has become a single steady thread that drifts without hurry. A quiet recap eases the thoughts, a rare birthplace raises a giant, the same forces that feed it also trim it, and the result is a brief life that fits limits rather than strains them. Elements forged inside drift outward, and the nebula keeps them safely for later worlds. Dust warms along rims, molecules rest in cool folds, and new stars wait at the edges like seeds pressed into soft earth. Tools that once struggled now read the page cleanly, and numbers that once swung now gather on a calm plateau. The cluster remains busy, yet the picture is clear enough to set the mind at rest. The large Magellanic Cloud fades to a distant lantern, and the wider galaxy becomes a quiet hallway beyond it. Nothing urgent presses. The furnace burns as it should. The wind carries only what it must, and the future approaches by patient steps, not by leaps. The image lingers a luminous hearth in a vast chamber, steady, and contained, sending warm strands of light along carved pillars, while fine dust falls like slow snow. The narrator's eye lifts to the larger darkness that holds everything in place. In that space, the rules that govern giants also comfort smaller lives because they are orderly, repeatable, and kind to patience. The last thought is simple and soft. Even the brightest blaze belongs to a pattern that rests, and in that pattern, quiet returns like the tide.